Hi folks, and welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to concepts of impulse and momentum. So what I'd like to do here is just kind of focus on the left on this object right here for just a moment. So imagine this is some object or system, whatever it is, and this system has a bunch of forces acting on it. So if we're to draw a free body, we might have a force that we call something F1, another one acting this way, maybe F2, and maybe a third one acting this way, F3. Now, after drawing the free body and adding these force vectors up, these force vectors would have some sort of net force, and the net force you would find by adding the x components, then adding the y components, and applying Pythagorean theorem. After doing so, suffice to say, we will get some sort of force. Roughly speaking, with the pictures I have, the net force would point maybe something like this. Right, so this video is not really about how to find the net force, but it's important to take note that that force does exist. So we have a bunch of forces acting on this mass. Those forces have a vector sum equal to what we would call the net force, which is that guy right there. Right, and now what we're going to do here is get rid of. Oops, where's my? Oh, there we go. Alright, so we're going to get rid of this guy here now. We don't need it anymore for the discussion. Okay, and we're just going to focus on this guy now. So, any given system will have a net force acting on it. I'm just going to move this to the center here for discussion. And, the relevant piece of mathematics to apply to this is Newton's second law. So, when we apply Newton's second law to this, what we have is that the net force is equal to mass times the acceleration of the system. Now, the acceleration can be written a couple of different ways. One of them would be this: acceleration is equal to delta v over delta t. And this fraction, this delta v over delta t, can be separated. If I wanted to, I could put that delta t onto the other side. So this thing is going to read now, if we do that, this is going to read f delta t is equal to m delta v. Right, and then simplifying this down a little bit more, the delta v, if we wanted to, we could write that v final minus v initial, because delta anything is always final minus initial. And this equation now, if I rearrange it just a little bit here, we can write it like this: m v initial plus f delta t is equal to m v final. All right, and we got that just by taking this mass, multiplying by these two terms, moving the m v initial to the left. So this equation here really is just Newton's second law, kind of twisted around or looked at sideways. I always like to say. And these terms, specifically this guy right here and this guy, mass times velocity, is called momentum. So I'll go ahead and write that down. Mass times velocity is momentum. Right? And then this product right here, force times time, that has a special name as well. That's called impulse. So force times, oh boy, I can write that a little better than that. Force multiplied by time, right, is equal to impulse. And this equation is fairly simply saying this, right? This term right here, m v initial, that represents the initial momentum of the system, whatever that is. M v final represents the final momentum of the system, and this quantity right here is the impulse, which changes the momentum of the system. So this equation right here, I'm going to write this out up higher. M v initial, I guess I don't need the initial on the mass. M v initial plus f delta t equals m v final. And what this equation is saying is, okay, my system has a certain initial momentum. Add to that the impulse, you get the new final momentum. Now, some important things to consider here. Well, one, look at the product mv. That's a scalar times a vector. Well, it turns out, I'm going to go ahead and put vector symbols on these. A scalar times a vector is a vector. So this momentum equation is a vector equation, and that means it can be applied in directions. All right? Let's talk units. So mass times velocity, this would have units of kilogram meter per second. So that's the standard unit of momentum, kilogram meter per second. For whatever reason, momentum never got its own little pet name or unit. That's just the unit for it, kilogram meter per second. Impulse here would have units of Newton seconds because it's force times time. And if you work out what a Newton second is equal to, it's equivalent to a kilogram meter per second. Remember, by Newton's second law, a Newton is a kilogram meter over second squared. And of course, this term over here would have units of kilogram meter per second as well. So this relationship is basically saying, again, it's important to understand conceptually what it's saying. A system will have a certain initial momentum. Add to that the impulse acting on the system, where the impulse is the net force times time. You now have the new momentum of the system. Now, there's a couple of cases where this is really a beautiful thing for us to have, and that's the case where we're looking at impacts. So I'm going to take a moment here and clean my picture up and draw what an impact problem might look like. All right, folks, I'm back. I got a picture here, and humor me and let me tell you kind of what this picture is. So imagine we've got this object here that I have red, and it's moving to the right at maybe, I don't know, 10 meter per second or something. Doesn't matter the actual number for the calculation or for the video here. And whatever its velocity is, I called that VR1, which stands for velocity, red mass, picture 1. Right? Right here we got this green mass, it's just sitting there. So its velocity would be 0, therefore not labeled. Now imagine that the red mass hits the green mass and becomes stuck to it, right? So the second picture here is after the collision, where the two masses are both moving to the right. I put VRG2. RG means the velocity of red and green. They're stuck together, right, in picture 2. And you know, if this were a class, I would go ahead and do a demonstration. For now, I'm just going to have you imagine this. If these masses were equal, if the mass of the red was equal to the mass of the green object here, what you'll find is that velocity gets cut in half. So for example, let's say this ended up being 10 meter per second. This one would be 5 meter per second. If this initial one was 20 meter per second, this one would end up at 10 meter per second, and so forth. It's pretty easy to set up an experiment to show that, if those masses are the same. And if we were to draw a velocity graph now, I'm going to go ahead and do this color-coded. I'm going to put them both on the same graph. The velocity of the red mass is starting out, as time goes on, VR1, whatever that is, it's some value. And then there's going to be this short time frame where it's hitting this green mass. And it's important to realize that time frame where that velocity is changing is pretty small. It might be something like 1/10 of a second or so. But basically, it gets cut in half. So the graph might look something like this, where the VR1, whatever its numerical value, would be constant until it hits the green mass. At that point, in a very small time frame, it would cut in half, and then it would be constant again. If I were to draw a velocity graph for the green mass, and I'll go ahead and do this in green, right? So the green mass at first is not moving, so the first little bit of that graph is looking like this. Then there's this small time frame where the green and red are changing in velocity. Right? And then boom, they'll have the same velocity now. Right? So the graphs are looking like this. The impact is occurring in this region. Graph-wise, it's all about what's happening right in here. And it's pretty easy to show that the slopes of these lines are exactly the same in this example, other than one is plus and one is minus. So the slope is telling us that the accelerations are the same, other than direction, and these have the same masses. So the force exerted on these masses during this small time frame, and again, it's important we're talking about just during this stuff right in here, the forces would look like this. You know, we've got a red mass here, right? And if I drew a free body during the impact time, we've got, you know, it's the gravitational force down, normal force up. There's some sort of force between the red and the green. It's a normal force. it would be this way on the red. I'm going to put N, how about RG, for the normal force between the green and the red. Okay. Now I'm going to draw a free body of the green mass during the same time frame. We've got the mg down. We've got a normal up. And this force right here that's left on the red mass, that exact force is right on this mass. Normal RG. And I'm going to go ahead and take a moment and just color code these because I think it kind of looks cool, makes the pictures kind of pretty. So there's our green mass. Right? Or there's our red mass and there's our green mass. So again, the important thing to consider here is this. During this small time frame, this stuff right here, that might be just 1/10 of a second or 100th of a second. That's where these free bodies are good. And if we look at the red mass individually, and we ask ourselves, is there a net force on the red mass? The answer is yes. All right, the normal and the mg may cancel, but there's nothing to cancel that sucker. So if our system is the red mass only, there is a net force. Another thing to consider, is there a net force on the green mass? And the answer, yes. These two, the normal and the mg, sure, these are going to add to 0, but there's this guy right here with nothing to cancel it. So if we define our system as just the green mass, then there is a net force. However, if we decide to define our system as the pair, this force is an internal force. Even if you try to include it, the vector sum is 0. So it's very, very important to note that as long as we define our system as both of them together, that the net force on that system is 0. And going back to our momentum concepts basically said this. mv initial is the initial momentum of a system plus F delta t, that's the final momentum of the system, or I'm sorry, that's the impulse acting on the system, is equal to mv final. So again, the initial momentum of the system plus the impulse acting on the system equals the final momentum of the system, right? If we applied that relationship to the red mass only, we would have an external force. If we applied it to the green mass only, we also would have an external force. A key concept here is that as long as we apply this to the system, the net force is system, and there is therefore no impulse. That allows us to say this: the initial momentum of the system is equal to the final momentum of the system. Allows us to write a nice, easy equation. I'm almost out of room here. I guess I'll write it right here. The initial momentum of the system is equal to the red mass times the velocity I called VR1. That's mass times velocity. That's the total momentum in this picture. There's only one term because only one thing is moving. That has to equal the total momentum after the impact. So that's the total momentum in this picture, which is equal to, now, treating these like one object, they're stuck together in this example. The total momentum of the system is mass of the red plus mass of the green, right, times the velocity, which I called VRG2. You could just call that V2 if you wanted, or V final or something like this. I wanted to take a note that that velocity is good for the red or the green in this example. If these masses are in fact the same, this would divide out, and what we would have is VRG2 is equal to 1/2 of VR1, which is the correct mathematical solution for problems that look like this. Now, this was a very, very, very simple example, but the key fundamental of this example will hold for much more complex problems. And the key fundamental is this, right? Momentum is mass times velocity. Whenever you have a system that has 2, 3, 4 masses, doesn't really matter how many, and they collide with one another, as long as we consider all of the masses at the same time as our system, we can write an equation equating the initial momentum of the system before impact to the final momentum of the system after impact. And in a lot of these, that'll be a one-dimensional type of equation, but again, it can be 2 and even in 3 dimensions. So that's the key concept here, that for impacts, generally speaking, what we'll do is we'll draw a picture before the impact, That'll look something like this. We'll draw a picture after the impact. That might look something like this. In this example, these were stuck together. That's why there's only one velocity vector, but they don't have to. You may see an example, or you will see examples where these are not stuck together and you have two different velocity vectors. Then, defining our system as both masses together, what we'll do is we'll write an equation equating the total momentum before the impact equal to the total momentum after the impact. So I think I'll save more examples of that for a second video, but that's about all I want to cover right now. So I hope this helped introduce you to what momentum is. It's mass times velocity, and at least give you an idea of how we're going to use it. Mainly, we will use it to analyze impacts by setting the momentum of a system before the impact equal to the momentum of the system after. All right. Have a great day.